I'm from SLAC, the laboratory at Stanford, and I guess I'm the author of this quantum field theory book that you guys used last year. So you probably already have some idea of who I am. I'll try not to dispel that idea as we go through this course. This is a course in elementary particle physics. In the tradition of the Psi school, what I'm going to do is in the next 3 weeks dump all of elementary particle theory on your head, and we'll see what sticks. So that's the plan. More seriously, what I'm going to try and do is to explain to you the structure of what we call the standard model of particle physics. And I'm going to have a lot to say about why we think the standard model is true. And so I hope that if that part of it sticks, I'll really be very happy. The standard model is a very beautiful thing as a set of equations, but it's even more beautiful when you see how it actually works with experimental reality. So I think the way this school is structured, when you come back after Christmas, everything you've done so far is pure theory. And now we have to learn a little about, the real world and what experiments say and how that jives with theory. And so that's going to be a big theme in this course. So the plan of the course is more or less like this. Today, we just need to get some orientation to elementary particle physics. So I'm going to tell you what the elementary particles are, or at least some of them. In the next lecture, because we're going to talk about experiment, and because I'm going to show you some experimental data, it'll be interesting to understand how that data is collected. And so I'm going to give you a lecture on particle detectors, how they work, what the basic types of particle detectors are, how you assemble them into these giant things like the detectors at the LHC. Then on Wednesday, we'll start in the standard model proper. You've all had a little exposure to quantum electrodynamics. So the first topic is going to be the theory of the strong interactions. So the first thing I have to tell you is why the theory of the strong interactions is simple, then why the theory of the strong interactions is not so simple, and finally we'll try and develop quantum chromodynamics to the point where we can actually write down the Lagrangian and understand why it's true. Then we'll talk about the weak interactions, the W boson, the Z boson, and all that stuff. And again, there's not only a very beautiful theory, but a very beautiful set of experiments that probe that theory quite incisively, and we'll talk about those. And finally, at the end of the course, CP violation, the top quark, and the Higgs boson, if we get there. There will be 3 problem sets in this course, 1 each week, and the first one I hope I'll get out to you tomorrow. Last year, I gave very long problem sets. I think Callum told me that some people handed in all of their problem sets in May, which they were required to do to get credit for my course. So I'll try not to make the same mistake this year. The problem sets, though, will be the minimum. For those of you who are actually really interested in elementary particle physics and you want to work harder, there's lots more you could do. And you'll find me in the corner office upstairs. I'll be there more or less all the time for the next 3 weeks. So if you have a question about the subject, drop in. And if you want to do more work, let me know. I'll give you more work. No problem. One more thing. Because I want to show you some experimental data and other pictures that have to do with experiments in elementary particle physics, I put some figures on, well, they're now on the web in some obscure place, but you'll find them on the wiki as of tomorrow, probably. So it would be useful if you folks would bring your laptops to class. And then I don't have to work the projector. I can just tell you, please look at figure such and such on the wiki, and you'll see where it is. There's a set of figures associated with each set of lecture notes. The lecture notes are also the ones that I wrote up last year when I was here. We'll go through them with a slightly different emphasis this year. But I think you already have the complete set of lecture notes, and Callum will put it on the wiki in the next day or so. Okay. Oh, one more thing. For those of you who are remote, because these lectures are being videotaped, the lecture notes and these figures are actually available in a public location. And to find that, you should go to the following place. My public web page is the following place: www.slack.stanford.edu/mpeskin. And if you look for the link for my courses at the top of the page, that'll point you to the Psi course. And all of the lecture notes and figures are available there. I'm not talking to you folks because they're taping these lectures. For those of you who are remote and you want to find these materials. For you guys, it'll all be on the wiki, so don't worry about it. OK. Any questions about procedure before we get to the actual stuff? OK. So what we're going to be talking about in this course is elementary particle physics. And so probably the first thing I should do is try and give you somehow a list of elementary particles whose properties we're going to try and understand. So I'm not going to give you a complete list right now. Let's just start off with the basic matter particles, out of which we're going to try and build our theory. In general, in the Standard Model, there are two components. First of all, the matter particles, the so-called quarks and leptons. And secondly, the forces, which are mediated by vector bosons. In fact, the very beautiful thing about the Standard Model is that it has these two components. Matter, which is composed of some spin-a-half fields, and these are called quarks and leptons. And on the other hand, forces, which are mediated by spin-1 fields, and these are the vector bosons of various types. So I think in this lecture, I'm going to give you an introduction to these guys, and then in the rest of the course, I'm going to try and write the equations for these various vector boson fields. What's beautiful about those equations is that they're all of the same type. They're all Yang-Mills theories. You folks all know what Yang-Mills theory is, right? Yes. And so one uses those Yang-Mills theories in different ways, basically picking up all the different properties of Yang-Mills theory in various regimes to explain all of the forces that we see in elementary particle physics. Of course, I need to point out that there are some extra things that are not written here that are also extremely important. One of them is gravity, which is mediated by the graviton, and maybe other stuff. And that's a subject that I'm not going to discuss in this course, but I presume in your other courses you'll hear a lot about that, maybe even about this. And then there's also something else that you need called the Higgs boson, or the Higgs field, and the Higgs boson. And maybe lots of other stuff. And this much of it we're going to talk about in this course. And again, this thing here you'll talk about in other later courses this year. So these things lie outside the domain of this course, which is basically on the Standard Model. But necessarily, you see, we'll have to say something about what the Higgs field is, what it does, and what its bosons' properties are to complete the story. And hopefully I'll get to that before the end of the course. OK, so in this lecture, matter, quarks and leptons. Oh, now, when we talk about the identities of elementary particles, there are certain things that are assumed. Maybe I should try and make them a little explicit. I've already noted that every particle has a spin. And more generally, every particle that we're going to talk about is associated with a field. So we're talking about very high energies, relativistic particles, and so the context in which we're working is relativistic quantum field theory. So in relativistic quantum field theory, the structure is that there's a field, and for every field, there's a particle. Now, in fact, for every field, there's a particle and an antiparticle. That is, you have a field phi. It might have a Hermitian conjugate phi dagger. Phi destroys some particle, and it creates another particle, which is called the antiparticle of the particle P. What this means is that P bar and P have the same mass because they come from the same field, which obeys a single field equation, and they have opposite quantum numbers in every respect. So the thing that destroys this creates that means that whatever quantum numbers this has the same quantum numbers, and this has the opposite quantum numbers. And so when I write down a particle, I always am talking about this duality of a particle and an antiparticle. And you just have to realize that as we go on. These particles have some other quantum numbers, and we'll talk about those quantum numbers as we proceed. Maybe it would be good to put some quantum numbers on the table now just for orientation. There are basic space. So first of all, we always assume Lorentz invariance. In addition to Lorentz invariance, there are some basic space-time symmetries that maybe or maybe not you folks have learned about, which are called P, C, and T. P is parity. That is to say, inversion of space. X goes to minus x. T is the inversion of time. T goes to minus t, running the equations of the world backwards. C is the inversion of particle and antiparticle. And so it's always interesting to think about, so these are basically three discrete symmetries. They all satisfy p squared equals c squared equals t squared equals 1. And you can use those to classify various aspects of the fundamental interactions. In particular, the electromagnetism and the strong interactions are invariant separately to P, C, and T. And so you can give particles definite quantum numbers under each of these symmetries. The weak interactions, very interestingly, violate P and C, and actually also T. And that's a subject that we'll have to go into in some detail about halfway through the course. For the moment, we're going to talk about the strong interactions and electromagnetic interactions. And so each of these is a good symmetry. And at appropriate points, I'm going to tell you what the quantum numbers of various particles are. You can work out those quantum numbers experimentally by seeing what the selection rules are. For example, if you have a particle that decays to two other particles, the form of the decay amplitude, the quantum mechanical amplitude for the decay, will be restricted by these quantum numbers. And so maybe I'll just quote them. If you want, you can ask me how those things are worked out. OK. Now, let's then begin with this catalog of particles. What I'd like to do is to write down the basic spin-a-half particles in nature, the quarks and leptons. And it's certainly easiest to begin with the, now there's one more piece of introduction I have to give you before I write that down. Then the next question that I'd like to discuss is, how do we identify these fields and write their field equations? So for a scalar field, a field of spin 0, it's really easy. It obeys the Klein-Gordon equation. over here we might have some nonlinear interactions. And there's not much to say about the Klein-Gordon equation. You could say we could make it simpler by setting the mass equal to 0. Actually, that doesn't make it simpler for reasons that I'll explain a little later in the course. For a spin a half, the way you probably learned it is you write the Dirac equation. And then you get a massive spin a half particle. However, I hope you also learned, at least if you looked at my book carefully, you learned this, that the Dirac equation is actually a composite of two equivalent equations that are kind of knit together. So if you write the Dirac matrices in this chiral basis, in this form, where sigma is 1 sigma and sigma bar is 1 minus sigma, then, and you set the mass equal to 0, then the Dirac equation falls apart into two simpler equations called the Weyl equations. Where psi right and psi left are two-component objects. Now, it's these objects that are the simplest from the point of view of Lorentz invariance. These two-component objects form irreducible two-dimensional representations of the Lorentz group. The mass term basically mixes these two guys into a single object, which is a four-component object. But for many purposes in elementary particle physics, and in particular for understanding the standard model, it's useful to go back to these relatively simple objects and take those as the basic ingredients. This is especially important when we're discussing the weak interactions. But I think I'd really like to start off here and get you in this frame of mind. Now, there's one more interesting property of these equations, which is that they're actually equivalent. Namely, if you write psi r psi L bar is equal to psi r star times sigma 2, the number 2 Pauli matrix. I don't know whether you want to put an I here or not. Let's put an I. Then this object obeys this equation if this object obeys this equation. So we can think of all of the spin-half objects in the world, as long as they're massless, as being psi L's. And we can just write a list of psi L's that represent all of the matter contained in elementary particle physics, all of the quark and lepton matter. This, it turns out, is an extremely useful thing to do. And let me get you oriented in that way. So the content of psi L is a left-handed fermion. That is to say, a massless particle whose spin is in this orientation, and its antiparticle, which is a right-handed fermion. That is to say, something with the opposite quantum numbers spinning in the opposite direction. Yes?
So where did the mass go?
Where did the mass go? I set it equal to 0.
Okay.
Okay. So that's why I'm allowed to do this. These particles are massless. They go at the speed of light, and they're spinning in some definite orientation. If I make a Lorentz transformation of a particle moving in the speed of light, it's always still moving at the speed of light. So I can't turn it around. And then its spin is either one way or the other. The spin is spin a half. It's quantized in some direction.
So
But
this whole trick with the Weyl equations doesn't work if we have a mass.
no, it's still, well, I'm going to say it's still useful, because what we're going to do with the mass is that we're going to take these as the basic particle states and we're going to mix them up in some way. So it's a useful way of thinking. And so now I can write the structure of quantum electrodynamics in this language. I have the electron, and the electron is now in two components. It's the left-handed massless electron, the left-handed massless positron. The antiparticle of this is the right-handed positron, and the antiparticle of this is the right-handed electron. This is all with zero mass. Now, if I turn on the mass, I'm going to mix up these two particles and get a massive particle, and I'm going to mix up these two particles. Now, why do I write things in this perverse way? Well, it's going to turn out when we study the weak interactions that these particles have different quantum numbers from these particles. And so, as I say, it's good to get oriented to this way of thinking as soon as possible. So fundamentally, these guys, the left-handed and right-handed pieces of the electron, are really completely different particles with different quantum numbers. And we'll see that coming in full force when we study the weak interactions. OK, so now let me try and, with that orientation, write a complete catalog of, first of all, the leptons. So there's a class of particles that we call leptons. It includes the electron. I'm going to call this guy E bar, if you don't mind. E and E bar. And there's one more lepton related to this, which is called nu, which is the electron type neutrino. The neutrino is a massless particle. The neutrinos are not massless, but let me. Okay, I'm going too fast. The neutrino is a neutral particle. It is associated with the left-handed electron. It's almost massless. In fact, one neutrino might be exactly massless. We don't know. And it's associated with the electron. And these three left-handed states are the content of the electron multiplet, if you like, in the Standard Model. For some odd reason, this multiplet repeats 3 times in nature. So there's another particle called the muon, which has a left-handed or right-handed piece and a muon-type neutrino. And again, a particle called the tau and a tau-type neutrino. I'm not going to talk about neutrino mass in this course, but let me just say that these 3 guys can acquire mass without actually requiring there to be a state nu bar. So in principle, these 9 Weyl fermions, these 9 fermions obeying the Weyl equation in the limit of 0 mass, is all you need to construct the Standard Model. Yes?
Is there something that tells us there's no more families below those 3?
People debate whether there's a 4th family. But there's good evidence that there are no more than 3 light neutrinos. We'll talk about that later in the course. These guys have, now when you turn on the masses, these guys have various masses. This guy has a mass of 0.51 MeV. I hope you're familiar with this MeV, GeV type of units. Roughly 1 GeV is the proton mass. And we'll use that as the basic unit of mass in this course. The muon has a mass of 105, I wrote it down here, 105.7 MeV. The tau has a mass of 1777 MeV. And why those masses are what they are is one of the big mysteries of particle physics. Nobody understands it. There's a story that Feynman tried to explain the ratio of the muon mass to the electron mass by thinking about the electron mass as coming from the muon mass by a quantum electrodynamics calculation. And within an hour, he had the right answer. And then he lamented, well, you have to think really hard, and the explanation is totally non-trivial. You know you have the right answer, but when you get the right answer right away, that means you'll never understand it. And in fact, to this day, no one really understands what this mass ratio is or why this guy is here. It's just somehow, maybe you guys can figure it out, that's the way that nature works out. The neutrinos have extremely small mass. They're probably much less than 1 electron volt. And I'm going to ignore the neutrino masses for the rest of the course, although we could discuss it privately if you like, how one determines this. Now, a consequence of this mass hierarchy is that the heavier leptons are unstable with respect to decay to the lighter leptons. So the muon, for example, decays to an electron and electron-type antineutrino and a muon-type neutrino. This is, if you like, the canonical weak interaction process. The weak interactions, as you guys all know, mediate radioactive decay of, for example, the neutron to the proton, or, in fact, the heavier leptons to the lighter leptons. And we're going to study this process in great detail when we get to the theory of the weak interactions. The lifetime is, well, kind of long on these terms. It's 2 times 10 to the minus 6 seconds, which is a whole long time in elementary particle units. A better way of writing it is that c tau is about 700 meters. So if you produce a relativistic muon in your detector, it'll go through the whole detector and just keep on going a very long way before it decays. We see muon decays in cosmic rays. We don't see them, and often we just see muons that haven't decayed in cosmic rays. The tau has many decays. We'll talk about them a little later in the course, but 2 of them are the analogs of the decay that I wrote up here. Tau to E, nu E bar, nu tau, and nu mu bar, nu tau. The lifetime of the tau is 0.29 picoseconds. A picosecond sounds like a very small unit, but it turns out then that c tau is about 1/10 of a millimeter. So a relativistic tau is almost macroscopic. And if you're very careful, you can catch these guys in flight and actually see that they go a finite distance before they decay. We'll talk a little about that tomorrow. The tau has other rather interesting decays. And when we get a little more equipment in this course, we'll be able to work those out. Okay. So this is almost all there is to say about the leptons. I'm going to say a lot about the structure of these weak interaction amplitudes. Other than that, the leptons all look like the electron. They obey quantum electrodynamics. They have standard electromagnetic interactions. The only difference between one and another, apparently, is the mass. And in fact, as we'll see, they have, with respect to the fundamental equations, the same quantum numbers repeated 3 times, and the same interactions as far as we can measure. One more thing I should say. Another decay that you might think the muon would have is the decay mu to E gamma. This seems to be perfectly allowed by all the quantum numbers that I've talked about so far. However, as far as we've seen so far, it doesn't occur. The branching ratio, that is to say, the fraction of the time that the muon decays this way rather than this way, is less than 10 to the minus 11. So somehow there's a principle that keeps these guys from turning into these guys we could say that each type of lepton carries a conserved quantum number, which is a symmetry all of its own. In discussing the Standard Model, we call these things flavor symmetries. In general, the difference between this, this, and this is called flavor. And from the point of view of what I'm talking about now, it seems as if there's an electron flavor quantum number, a muon flavor quantum number carried by this one has -1 and this, a tau flavor quantum number carried by this, and this. Why that should be, it's actually a prediction of the Standard Model in the limit of zero neutrino mass. And we'll discuss that in the last week of the course. It, however, requires that there has to be a different neutrino for each of these guys. Otherwise, you could probably write some process where you start with this guy. If these two neutrinos were identical, you could make them one annihilate the other. You'd end up with an electron. You radiate a photon from in here somewhere, and you can figure out how to mediate this decay. So the fact that this decay doesn't exist is part of the evidence that all of these neutrino species are actually distinct from one another. OK. Well, those are the leptons. They're easy. Now we have to turn to the quarks. Now, the leptons are easy because we can see them. The quarks are difficult because we can't see them. And in fact, it took a long time to recognize that the quarks are elementary particles. What one has instead are things that we call hadrons, the strongly interacting particles. And hadrons come in two types, mesons and baryons. Baryons are the most familiar strongly interacting particles. The proton, the neutron, and others of the same ilk in a way that I'll describe in a moment. Mesons include the pion, the kaon, and others. I'm going to make a long list for you in just a moment. In general, mesons are bosons, and baryons are fermions. And these particles can have various spin. So here we'll find spin 0, spin 1, etc. Here we'll find spin 1/2 and spin 3/2, and in fact even higher spin. The proton and the neutron, of course, have been known for a long time. They're the basic constituents of atomic nuclei, and they're the only stable baryons. All the other baryons will decay to them. All of the mesons that we know are ultimately unstable, although they're not necessarily unstable within the strong interactions. They all figure out how to decay somehow. Maybe we should start with the proton and neutron. So the proton has famously a mass of 938 MeV, so roughly 1 GeV. The neutron has a mass very close, 939. This is 0.3, 0.6 MeV. The fact that the proton is charged, and you know that a charged thing has an electromagnetic component to its mass, but the neutron's actually heavier. So you should think of that as something mysterious that I ought to explain. And I will try and explain it, but I'm not going to explain it completely. There's a part of this issue which we can just kind of push back one level, but after that we don't understand it. But already it's kind of strange that the neutral particle here in this, obviously a multiplet of particles, is heavier than the charged one. The proton, as far as we know, is absolutely stable. In fact, people have done quite interesting experiments on proton stability. The limit on the lifetime of the proton is, anybody know? Anybody want to take a guess? Yes. Sorry? No, the experimental limit. Obviously, you can't make an experimental limit of forever. If you watch a proton and you ask, does it decay during the time of the experiment, what kind of a number can you get?
Something like 30 billion years or something.
Well, we know that protons are still around since the beginning of the universe, so it's got to be larger than 13 billion years. But you can actually take protons and watch them. In fact, you can imagine that you could watch Avogadro's number of protons for a year. And if you have a very sensitive detector, if one of them decays, you would probably notice. And so that should give you a limit of about 10 to the 23 years, which is much bigger than the age of the universe. In fact, the numbers here are really more like 10 to the 30 years, because you can watch, like, for example, big tanks of water underground. And so let me just quote you two impressive numbers. If you look for specific decay modes, one that you might want to find is the decay of a proton to a positron and a neutral pi meson. This is allowed by all fundamental symmetries. And this lifetime is greater than 1.6 times 10 to the 33 years. So the proton is impressively stable. The lifetime for a proton to go to some invisible mode, invisible to the detector anyway, there always has to be a charged particle in the final state, but it might be a very low energy electron that you couldn't detect. This is greater than 2 times 10 to the 29 years. So the proton is impressively stable. And to, quote, explain this, we postulate a quantum number called baryon number conservation, that the total number of baryons in the universe is always conserved. Baryons can turn into one another, but they can't just disappear into leptons and energy. Why this should be is something that we ought to explain in our theory. And maybe I should say that it will be a property of the standard model, but it isn't really explained. It's more like it's postulated. Other theories actually predict proton decay. We'll talk about that maybe a little in the last week of the course. Now, the neutron can... Yes?
There are many theories of the end of the world.
Yes?
Like the thermal death of the universe. But they
Yes.
all say that in the end, even the protons will decay. But does this theory actually say that in the end there will be protons?
You have your choice. There's some theories in which the thermal death of the universe just involves a lot of cold protons, or cold atomic nuclei, actually, because atomic nuclei are stable if the proton is stable. And there are other theories where the protons all decay, and all we're left with are electrons and photons. And you have your choice. I'm rather in favor of the latter, that protons do decay, and that eventually we just end up with electrons and photons. But it's a long way from now. I mean, long after the universe becomes totally cold and quiescent. So it's not something you have to worry about. There's a Woody Allen movie where among the other malaises that he's discussing, he finds out that protons decay. But you don't have to worry about, really. Many worse things will happen before that. Okay, the neutron, however, does decay. Maybe I should say a neutron outside of an atomic nucleus. A neutron can be stabilized by its binding energy because it's only an MeV above the proton, and it can have a binding energy of order 10 or 20 MeV in a nucleus. But a free neutron decays, famously by beta decay, to a proton, an electron, and an electron antineutrino. And the lifetime here is 886 seconds. So again, a very macroscopic timescale. Interestingly, the cosmic fraction of helium versus hydrogen in the early universe is sensitive to this number. And it comes out right by virtue of that number being what it is. So there's actually some kind of cosmic significance to the decay of the neutron. roughly in the early universe, you have to make sure that helium gobbles up enough neutrons before the neutrons decay. And that tells us some things about cosmology at essentially a couple minutes after the Big Bang. Okay. So these are the two basic baryon states. I'm going to write down a lot more in a moment. But let me first turn to the mesons. They're a little simpler. In addition to the proton and neutron, it was discovered that there are many other strongly interacting particles. And the first ones to be discovered were these mesons, the pion, the kaon, etc. Let me tell you a little about their systematics. The pion, there are 3 of them, all of roughly the same mass. Pi plus and pi minus have a mass of 139.6 MeV. The pi 0, 135 MeV. So the masses are quite similar. It's suggested that these things belong to a multiplet under some quantum symmetry. Notice that in this case, the charged particles are heavier than the neutral one. So that's what we expect for an electromagnetic correction going from here to here. And in fact, if you compute that electromagnetic correction, you actually get the right answer. The mass difference between these guys and this guy is explained by the fact that the charged guys can communicate with a photon and get a little mass from that effect. The neutral particle, all these particles are stable with respect to the strong interactions. And maybe I should also say they have odd parity, intrinsic parity. So intrinsic parity means if you act P on that state, you get a minus sign. P acting on a 1 pion state gives a minus sign. And that's interesting from a point of view that we'll discuss in just a moment. These guys are stable with respect to the strong interactions. They're actually the lightest strongly interacting particles. They decay, though, through electromagnetism and the weak interaction. The pi 0 decays to 2 photons, 2 gamma rays. It decays very quickly. Its lifetime is roughly 10 to the minus 16 seconds. Actually, even c tau is nanometers, 10 to the minus 8 meters. So in an experiment, you would never see a pi 0. You just see the 2 gamma rays that come from the pi 0. The pi minus and the pi plus are more long-lived. These decay to a muon and the neutrino, a muon-type neutrino, or an electron and an electron-type antineutrino. The lifetime here is 10 to the minus 8 seconds, which means that the c tau is macroscopic, 7.8 meters. In cosmic rays, you see pions at high altitude. Typically, they don't make it all the way down to the Earth's surface unless they're very relativistic. Interestingly, the pions usually decay to muons. They practically never decay to electrons. The branching ratio is about 10 to the minus 4. So you might ask, that's really weird. You just told me that the electrons and the muons have exactly the same quantum numbers. They only differ in mass. And typically, it's harder to decay to a heavier thing than a lighter thing. So why is it that the heavier thing is the one that you decay to most often, and the lighter thing, you hardly ever decay to it at all? And this is one of those things that I can explain. And when we study the weak interactions, we'll have an explanation for that. OK. Beyond these light states, the pions, the protons, and the neutrons, there's a huge variety of hadrons. And if you only deal with fundamental physics, maybe it isn't so important to know what all those particles are. But if you actually observe elementary particles, you see all of them. So it's important to know what they all are. And so, well, you just have to learn it. It's like botany. Something that's very useful is that at Lawrence Berkeley Laboratory, they collect hadrons, and they put them in a big book called the Particle Data Book, which by now is more than 1,000 pages long. It reports all of the known hadrons and other particles like the leptons, bosons, etc. Gives their properties, gives lots of useful references. It's a great reference. As I said, the project was started at LBL by Arthur Rosenfeld in 1957. Now it's managed by a big international collaboration, still centered on LBL. This collaboration is called the Particle Data Group. And I think every serious elementary particle physicist has a copy of the Particle Data Group reference book on his or her desk. Actually, the Particle Data Group also puts out a little handy reference booklet. And it used to be a wallet card, one card. Now it's a little booklet of about 100 pages. But it fits in your backpack. Personally, I carry it everywhere. When I was a graduate student, I used to bring the Particle Data Book to seminars. And whenever an experimentalist speaker would say something that I didn't recognize, I'd look it up in the book. A very good exercise. I strongly recommend that to you. This booklet is free if you register and write to the Particle Data Group. And I strongly recommend that all of you who are interested in elementary particle physics should do this. We'll dip a little into this book tomorrow for the information that it has about the properties of particle detectors. Okay, so now, having told you where to get this information, what I'd like to do is to give you some, just make some lists of hadrons, and then I'll talk a little about how they're organized. So, I told you that there are many types of mesons. These particles are all bosons, and all of the lightest mesons have odd intrinsic parity like the pion. There's actually two groups of 9 that are very prominent. First of all, pi plus, pi minus, and pi 0 with a mass of about 135 MeV. Then 4 particles called the kaons. Maybe I should say that pi plus and pi minus are the antiparticles of one another, and pi 0 is its own antiparticle. For the kaons, there are actually 2 neutral kaons, which are the antiparticles of one another, and k plus and k minus. These have a mass of about 493 to 97 MeV. And then there are 2 other neutral particles called the eta and the eta prime at 547, and this is about 900 MeV. These particles all have spin 0, and they all have odd parity. Then there's another group of particles with spin 1 and odd parity. Again, 9 of them. Rho plus, rho minus, and rho 0 with a mass of something like 770 or 775 MeV. A particle called omega, very close at 810. A multiplet of particles called k star, just like this. 4 particles, which are 2 particle-antiparticle pairs at, oh, sorry, I remembered that wrong, 782. These guys are at about 890. And then a particle called the phi, which is at 1019 MeV. Again, if you want the exact numbers, you can look them up or look in my lecture notes. The fact that there are 9 and they organize themselves in this way, we'll discuss in just a moment. On the baryon side, one also finds 2 prominent low-lying multiplets. One of them contains the proton and the neutron at, again, about 930, a neutral particle called the lambda, which is at 1116, a triplet of particles called the sigma, which is roughly 1180 to 90, and two particles called the cascade particles, or Xi particles, at about 1300. And these all have spin 1/2. And then a multiplet of particles which have spin 3/2, called the delta. There are 4 deltas, beginning with spin +2, charge +2, oddly, at 1232. 3 sigma stars, 2 cascade stars, plus 0 and minus, 0 and minus, and a particle called the omega minus, which has mass 1672. And if you look at this, there's roughly equal spacing in this multiplet between these guys, this, and equal spacing between this, and this, and between this, and this. In fact, this equal spacing rule led to the postulate of the omega prime. And people looked for it very carefully in bubble chamber experiments and found just a few events. And it was a spectacular discovery in its time, I think 1962, when people thought they were actually beginning to understand the systematics of these things. Yes?
What does it say with decays and also?
Oh, sorry. Here?
Yes.
Oh, I'm sorry. It's the same as this. K plus, K0, K0 bar, and K minus, except these are called K star. And they're different particles. They have spin 1. Okay. And similarly here, it's sigma with spin 1/2, and these guys here all have spin 3/2. Okay. And then there are various symmetries that are apparent in this table. For example, these guys all have the same mass. These guys, too, very close to the same mass. I've told you that in the pions, the mass difference here is just given by an electromagnetic effect that one can compute. So it's useful to group these particles together. And in fact, there's a symmetry of strong interactions that relates these particles. So going back to nuclear physics, actually Heisenberg recognized that you can group the proton and neutron into a doublet. And there's a symmetry that acts on this doublet. For example, a unitary matrix that interchanges P and N. So this is actually an SU2 symmetry, which continuously rotates P into N. And this, Heisenberg realized, was an approximate symmetry of the strong interactions of nuclear physics. This symmetry is called isospin. So it's a kind of fake rotational symmetry in which you call the proton the spin up particle and the neutron the spin down particle in a multiplet. And it turns out that the interactions of nuclei, if you ignore electromagnetism, which is a small effect in light nuclei but a large effect in heavy nuclei, are invariant, approximately invariant to this symmetry. For the present purpose, yes?
The cascade things, there's
Yes.
a minus, but there's no plus. Shouldn't it have an anti-particle?
Oh, I'm sorry. These are all baryons. And then every baryon has an antiparticle which is an antibaryon,
Oh, you're just not writing them.
which I'm not writing. So there's a p bar and an n bar. The p bar is negatively charged. And these guys have antiparticles called this. And this guy is positively charged. It's the antiparticle of that. Similarly here. Okay. These guys carry baryon number -1. So an antiproton can annihilate a proton into nothing. And that doesn't contradict the fact that an isolated proton lives forever, or as far as we can tell. Okay. Yes?
What do you mean by this? Something must be invariant on the symmetry, so what do you...
Well, I guess the way you would see it in nuclear physics is you can classify nuclear energy levels in terms of SU2 rotational multiplets. But here we'll classify the elementary particles in terms of these. So you know in rotational symmetry, you have multiplets of 1 for a scalar, 2 for spin 1/2, 3 if you have spin 1. So these particles also have those laws. So for example, these guys form an isospin 1 multiplet. So it's spin 1 under this fake rotational symmetry that rotates these two guys into one another. These guys, turns out, are isospin 1/2. These guys here are isospin 3/2 in addition to being spin 3/2. So the way you can see that is you can actually take a proton or a neutron and a pion, pi plus, pi minus, and pi 0, and collide them and form a delta resonance, which then decays back to some combination of proton and neutron plus one of the 3 pions. And the amplitude for these to make these are exactly in the ratio of SU2 Clebsch-Gordon coefficients. So here you have a Clebsch-Gordon coefficient for spin 1/2 and spin 1, M1 and M2, to spin 3/2 and capital M. This process is described by a single overall amplitude times this set of Clebsch-Gordon coefficients. And so from that, we know that isospin is a good symmetry of the strong interactions, and we can classify these particles into strong interaction multiplets. Okay. So now there are, well, hundreds of other hadrons, but I don't think I need to talk about them. What you really want me to talk about is how are these particles made up in terms of the truly elementary particles? And in principle, if I were giving a course in elementary particle physics, I would take a whole week to explain how the quantum numbers are worked out and what decays to what and what all the interrelations are. But I think in this course we have to move quickly, so I just have to tell you the answer. So it turns out that all of these particles that I've written on the blackboard are composites of spin 1/2 fermions called quarks. And the way their composite structure is worked out is probably made most clear by thinking about the delta here. So the delta is a fermion of spin 3/2. The way you would make it is to start with fermions of spin 1/2 and put together 3 of them. And so if I postulate a particle called U and a particle called D, which are spin 1/2 particles, and I put them together with 3 of them, there are obviously 4 ways to do it. I could have UUU, I could have UUD, I could have UDD, or I could have DDD. And if I align all the spins of these particles, I'll get spin 3/2 particles, and I get 4 of them. And if I insist that isospin, what it does fundamentally is to interchange U and D, then these 4 particles form an isospin 3/2 multiplet. And I've reconstructed exactly the structure of the delta. If I now postulate another guy called S, so these are also called up, down, and strange, then I can have UUS, UDS, and DDS. And these guys here form an isospin 1 multiplet, which is exactly analogous to this. Then we can just continue. USS and DSS, and finally SSS. that structure completes this triangular 10-fold multiplet of particles. Okay, now I have the spin 3 halves, but I could also make a spin a half combination of these. And from those, you can build this 8-fold multiplet. So everything is now fitting together. The proton and neutron are UUD in a spin a half. The neutron is UDD in a spin a half. And similarly, these would now contain one S, and these would contain two S's. If each particle number is conserved, then what you would say is that things with S can't decay to things with only U and D by strong interactions. And that's actually an observed regularity. These guys here can decay to proton and neutron, but only through the weak interactions. That is, only through very slow processes, not processes that take place essentially instantaneously. You can make sigmas from protons by colliding pions. But when you do that, what you get is a kaon instead of a pion. So this guy contains an S. This must contain an S bar. Let's see, if I have pi 0, p plus, sigma 0, let's say k plus, this guy here must contain the S bar. And so you can then start explaining these particles as particle-antiparticle pairs made out of these same particles. For example, pi plus is UD bar, k plus is U S bar. If I have 3 of these and 3 antiparticles, that makes 9. If you have 9 particles, 9 spin halves, you can organize their spins either into spin 0 or spin 1. And so that actually explains all of the particles that I've written here. The mass differences between this, this, and this, or this, this, and this, comes from the extra mass, which we would require anyway for the strange quark to have this kind of level segmentation of the mass.
Can't
Yes.
we get high-spin mesons with orbital angular momentum?
Oh, yeah. The heavier ones also have orbital angular momentum. So these guys all have 0 orbital angular momentum. That's why they're the lightest. Then they have excited states with orbital angular momentum. And if you look in the particle data book, you'll find lots of these things. People classify them in that way. Okay. I'd probably better wrap this up for today. I'd just like to tell you 2 more things about this. First of all, over here, the fact that these guys all have odd parity naturally comes from the fact that they are particle-antiparticle bound states. And Colin, I think, will explain that to you in the tutorials this week. Secondly, over here, where does this number 10 plus 8 come from? And it comes from an odd counting of these states. So maybe I should say, just for definiteness, these particles, UD and S, are called quarks. The rule for quarks is that their orbital states, obviously they can't be antisymmetric, because this guy here is U. Oh. We're running way over the hour. Let me finish this tomorrow. Shall I do that? I think John probably wants to get in here. Okay. Oh, let me say this for the whole course. You probably noticed already I have a lot of trouble stopping. So at 10 o'clock, you guys should start banging on the floor and telling me to stop. There's always another lecture. I'll finish this discussion of quarks tomorrow.